Okay, so what I wanted to do with this video is go over some material that we didn't have time to do in class yesterday, and hopefully that will help. So we're basically going to be talking about free fall. So free fall is a type of motion which is constant acceleration. In this case, the acceleration is due to gravity. Now, we remember that, well, I don't know if we remember, but we should know that when objects are falling, they accelerate towards the surface of the Earth. And so this is usually defined as the negative direction. And so that's the direction of the acceleration of gravity. The magnitude of the acceleration of gravity is 9.8 meters per second squared. And so notice that in the expressions that we see here, these are our kinematic equations. We would be replacing the value of acceleration by the acceleration of gravity. In this picture, we see a picture where they've taken the picture of a ball that's falling through the air, and the pictures are being taken at equal time intervals, and we see that the distance that the ball has traveled is increasing at every time interval. So we can see that the ball is accelerating because the velocity is obviously increasing between each successive picture of the ball. So from here to here, we see that the ball is actually going faster because it covers more distance. So when we talk about the equations for free fall, the equations that we had previously that we looked at for just constant acceleration, here they are. And essentially the changes that we make is because for these type of motions we were usually thinking about motion along the x direction. But for free fall, objects are moving up and down in the y direction. So one of the changes we make in our equations of motion is that the x direction changes to y. So we usually use y because it's more convenient. And the acceleration is equal to minus g, which ends up being altogether minus 9.8 meters per second squared. Just be careful that you don't put two negative signs in there. It should end up looking like the minus g corresponds to minus 9.8. So for free fall then, the kinematic equations that we're going to work with are y equals y naught plus v naught t minus 1/2 gt squared. V is equal to v naught minus gt, and v squared minus v naught squared is equal to minus 2g y minus y naught. And so you can see that if you are starting to feel comfortable and remember the equations of motion that we looked at for constant acceleration motion, it's very easy then to remember your free fall expressions because they're basically the same with those two minor changes. So when we talk about something that's undergoing free fall, what do we mean by the acceleration of gravity? So here, and for some reason we can't get superscripts and subscripts when we transfer these slides into this program, but the acceleration of gravity is 9.8 meters per second squared, or if you're using our unit of measurement, it's 32 feet per second. So in this picture here we have, okay, what would happen if we drop something from the top of the Leaning Tower of Pisa? You know, how fast would it be moving? What does the acceleration mean? The acceleration due to gravity means that every second the change in the velocity that experiences 9.8 meters per second. So in every second, the change in velocity is 9.8 meters per second, which is what acceleration means. So in this picture here, they want you to figure out what the velocities are and the position of a falling coin if it's just dropped from an initial velocity of 0. And so if we think about after 1 second, that's pretty easy. The speed will be minus 9.8 meters per second because it's only had 1 second to go. For my y expression, how far has it gone, or what is its y position, I'm going to use this expression, y is equal to minus 1/2 gt squared, and that's because y naught is 0 and v naught is equal to 0. And so we've put those expressions in for y naught and v naught, and then it leaves us with just this expression to calculate the y position of the object given different times. So if we let t equals 1, we'd have 9.8 times 1 squared, and then divided by 2. So, and this is going to be negative, so it's going to be minus 4.9 meters is its location. It's going to fall 4.9 meters. And the negative sign is because that's the negative direction. We're going to say in this slide, positive is up and negative is down. And this was our y equals 0 point. So everything below that has a negative y value. If we go then to 2 seconds, our velocity is minus 19.6 meters per second because it changes by another 9.8. In order to find the y position, we take time equal to 2, we'll square it, multiply by 9.8, divide by 2, and that also gives us 19.6 meters, and it's in the negative direction. And finally, the last one that they ask us to do is v3, so the speed at that point would be 29.4 meters per second, and the y position is going to be 3 squared times 9.8 divided by 2 is going to be minus 44.1 meters. And notice how these distances really do grow pretty quickly because of the acceleration of gravity. One of the things that is kind of interesting is when we talk about an object going up and down and falling under free fall, we might not have thought of this, but the motion is actually very symmetric if we're talking about leaving from the same location as we fall to. And so if this ball was initially thrown directly upward, it's going to rise into the air until it reaches its highest point. Now, something that we should realize, at the highest point, its velocity is 0. At all these points here, the velocity would be greater than 0. And then all these points on to the right, the velocity would be less than 0. But it's going to take the same amount of time for the ball to rise to the highest point as it takes for it to fall back down to where it started from. And so if it takes 1.53 seconds to go upwards, it's going to take 1.53 seconds for it to come down. And everywhere, if we look at this graph along a horizontal line, so the amount of time that it takes it to go, say, from here to here is going to be the same as the amount of time it's going to take it to go from here to here. And so it's going to be perfectly symmetric. Also, another thing that will be true is that the speed of the object is going to be exactly the same. The velocities will have the same magnitude but be opposite in sign. Okay, so here we're just going to do one quick example problem for how we might use our freefall expressions to solve a problem. And so, again, I'm just going to write them for us to remember. I'm going to change y equals y naught plus v naught t minus 1/2 g t squared, and v is equal to v naught minus gt. Now, we're saying small rock is thrown vertically upward with a speed of 22 meters per second from the edge of a roof of a 30-meter tall building. So we can draw a little picture. Here's our building. The height of it is 30 meters. The ball's being thrown upward initially at 22 meters per second. I'm going to let this be my y equals 0 at the bottom of the building. So that means that y naught is going to be 30. And my initial velocity is 22. And so putting in those initial values of the initial position and the initial velocity allows me to come up with these two expressions for position and velocity that are exactly, that will help us deal with any sort of problem, that will help us solve this particular problem. And so the two questions that are being asked is, what is the speed of the rock just before it hits the street, and how much time will it take from when the rock is thrown until it hits the ground? Okay, so sometimes you don't need to solve a problem in the exact order it was given. And so I actually think it would be easier to find this answer, and this answer is going to actually help me find the answer to the first question. Because I want to know how long the rock is in the air, which often is called the time of flight. And so then I have to ask myself, if the rock is going to go up into the air and then come back down, what I'm trying to find is, so how long does it take? Well, then I have to ask myself, when the rock gets to this location, what do I know is true? Now, a lot of people want to say, oh, well, the speed will be 0. That's not true. The speed will be 0 after it hits the ground, but it will hit the ground with a certain velocity. So we don't know what that is, though. But what I do know is that when it hits the ground, I do know what its location is. Y is equal to 0. So I'm going to use my y equation. And I'll set y equal to 0. And now I can find the time from this equation. And if you're thinking that I have to use the quadratic equation, you're right. So I'm going to go over to the next page so I have a little more room. And so I had 0 was equal to 30 plus 22t minus 4.9 t squared. I'm going to multiply by a -1, so I get 4.9 t squared minus 22t minus 30 equals 0. And I'm going to solve for t using the quadratic formula. So you do need to know the quadratic formula, you can't forget it. Notice this is going to give me two answers, and one of the answers is going to be negative. We can't use the negative answer because we can't have negative time, so our positive answer is 5.58 seconds. And so that's a situation where your the solution to the quadratic equation tells you mathematically there are two answers to this question. Your physics tells you that one of those is not relevant to this problem. And so I find out this is how long the rock is in the air. And now if I want to know the speed when it hits the ground, I use that time because that's how long it's flying. And I want to know what is the speed at this time. And I use my expression for velocity, and I get minus 32.74 meters per second, which makes sense because I know it has to be negative because as it's coming down, it's going in the negative direction. So hopefully that helped just to get a little bit of more explanation of free fall and also to see a problem solved.